We spend billions, I mean literally billions, laying down 5G networks across the globe, but the edge compute capacity inside those networks is just sitting there completely idle.
Oh, yeah, it's totally functionally brain dead.
Right. We have practically built the largest, most sophisticated distributed physical network in human history, and we've just left it empty.
It really is the ultimate architectural irony of modern infrastructure.
Yeah.
Because we have the plumbing perfectly laid out, you know. We have fiber trenched into almost every urban center on the planet. But we are absolutely terrified to put any actual intelligence inside the pipes themselves.
Which makes no sense when you think about it.
None. The telecommunications companies are essentially operating as highly optimized transit systems for data.
Just dumb pipes.
Exactly, just dumb pipes. While the actual value extraction, like the AI inference, is happening hundreds of miles away in a server farm.
So if you are an operator, right, or an engineer, or a systems architect tasked with testing and deploying edge AI reliability, this dynamic is the exact center of your world right now.
Oh, absolutely. It's the only thing that matters.
Because you are the one trying to bridge the gap between those pristine, climate-controlled cloud data centers and the gritty, chaotic physical realities of the real world.
Which is not easy.
No, it's a nightmare. So for this deep dive, we've got a fascinating stack of strategy memos, technical landscape reports, and architectural breakdowns.
Some really cutting-edge stuff in here.
Definitely. We're looking at a 2026 PatSnap Tech Landscape Report on AI inference accelerators, an AWS breakdown on distributed inference for SmartX telco deployments, and the top 10 edge management platforms for 2026 from Technology Radius.
And those founder-grade architectural strategy memos, too.
Oh, right. Those memos are incredible because looking at all this material together, it becomes immediately clear that there is a hidden war currently raging between the telecom companies and the cloud hyperscalers.
Yeah. And that war is literally the foundation for every technical hurdle operators are facing in the field today.
Let's break that down. Who exactly holds the power right now?
Well, if you look at the current power dynamics, the hyperscalers, AWS, Azure, Google Cloud, they completely own the control point.
Because they have the massive data centers.
Right. They keep the high-margin, heavy-lifting AI inference workloads completely centralized in their server farms. Meanwhile, the telecom operators—
The people who literally poured the concrete for the 5G towers.
Exactly. The people who built the physical network are just relegated to selling raw bandwidth. The memos actually refer to this as the dumb pipe dilemma, like you mentioned earlier.
So the hyperscalers just want the telcos to act purely as a delivery mechanism.
That's all they want. They want the camera on the street corner to stream all that raw data back to Virginia or Oregon so the cloud can process it, run the inference, and capture all the financial value.
But the infrastructure operators are finally fighting back, aren't they?
Oh, they are. Hard.
Because there is a massive shift detailed in the technical landscape towards something called agentic AI fleet orchestration over 5G MEC.
Right. Multi-access edge computing.
Yeah, MEC. So instead of sending all that raw, heavy data back to a centralized cloud, the telecommunications companies are attempting to shift the control plane directly to the base station itself.
Which is huge.
I mean, SK Telecom, for instance, they have a pending 2026 patent targeting the orchestration of AI services directly within the radio access network, the RAN.
Yeah, they are architecting a future where they completely bypass the centralized cloud for edge intelligence.
But why now? What's the forcing function here?
Well, they have to. I mean, from a purely physical standpoint, distance is a tax.
Distance is a tax. I like that.
It's true. If you have thousands of autonomous vehicles, industrial robots, smart city cameras, and they're constantly streaming 4K video and LiDAR point clouds back to a centralized server farm, you are paying an exorbitant tax.
In bandwidth alone, that's massive.
In bandwidth, in routing hops, and crucially, in latency. I mean, the speed of light through fiber optics is finite.
Right, you can't cheat physics.
Exactly. And the switching delays at every node, they add up. So the structural imperative of this decade is that you just cannot move the data to the compute anymore.
The data is just too heavy.
Way too heavy. You must move the compute to the data.
Which sounds incredibly logical if you're standing at a whiteboard.
Oh, in theory, it's perfect.
But the moment an operator tries to actually move that compute out to the edge, say, bolting a dense AI inference cluster onto a 5G base station, they hit a massive physical wall.
A literal wall of heat.
Yeah, because the true choke point isn't network bandwidth at all, is it? It's thermal management.
This is where the physics of the real world, just violently collide with the assumptions of software engineering.
Because software developers don't usually think about weather.
No, they never have to. A 5G base station is, at its core, a sealed metal box bolted to a pole or sitting on a concrete pad, completely exposed to the elements.
Right.
It absolutely cannot cool or power the kind of hyperscale-grade server racks you find in a massive liquid-cooled data center.
The strategy memos bring up this vividly practical example of this. The Nagpur summer heat.
Oh, that's a brutal environment for hardware.
Right, so Nagpur is a major city in central India where summer temperatures regularly push past 45 degrees Celsius.
Which is what, like 113 degrees Fahrenheit?
Yeah, about 113 Fahrenheit. So if you are an operator deploying hardware in that environment, you are dealing with ambient heat that is already pushing the silicon toward its operating limits before it even runs a single line of code.
Before you even turn the AI on.
Exactly. You cannot outcode a thermal bottleneck in a metal box sitting in blistering heat. If you try to run heavy transformer models on standard server chips in that environment, the silicon will literally melt its own solder joints.
Because, again, software developers historically haven't had to care about the physical temperature of the CPU.
In the cloud, the cooling is completely abstracted away. You just spin up an instance.
Right. You don't care if the server room is freezing cold or what. But at the edge, the software must now know exactly how hot a local processing unit is running before it decides to route a task to it.
Wow, so the software has to be physically aware of the hardware's temperature?
Exactly.
Yeah.
If the local CPU is hitting 95 degrees Celsius, the orchestration layer has to dynamically reroute that inference task to a neighboring base station that might happen to be in the shade.
Oh, that's wild. It routes traffic based on shade.
Or it has to lower the precision of the AI model on the fly to generate less heat.
So this fundamentally changes the historical power dynamic, because historically it was just the hardware OEMs and the cloud providers running the show.
Right.
But now telecom operators are fighting to become the primary edge infrastructure stakeholders.
Because they own the physical boxes.
Yeah, because if the operators can successfully build these lightweight, hardware-aware orchestration layer software that intimately understands the thermal limits of the specific physical box it lives in, they can steal the enterprise edge market right back from the hyperscalers.
And that right there defines the core actionable takeaway for any operator testing edge reliability right now.
Listen up if you're an operator.
Seriously, your first metric is not ping time. Your first metric is thermal capacity.
Not ping time.
No. If your testing frameworks are running in an air-conditioned laboratory in Palo Alto, your data is completely useless.
Because it doesn't reflect the real world.
Right. You absolutely must simulate high-load inference during peak environmental heat. You have to put the hardware in a thermal chamber, crank the ambient temperature to 45 degrees Celsius, and validate whether your hardware-aware routing protocols actually throttle and reroute traffic correctly when the sun is relentlessly beating down on the enclosure.
Wait, okay, so let me make an analogy here. This is basically like having a sprawling, massive mega mall outside of town where everything is perfectly air-conditioned and available.
Okay.
But it takes an hour to drive there. That's the cloud. The 5G edge, on the other hand, is like a tiny local corner store. You can walk there in 30 seconds.
Right. Super low latency.
But the corner store's biggest problem isn't that it lacks shelf space for the goods. It's that the refrigerators literally keep overheating and shutting down the entire store if too many customers walk in.
That is the exact mechanism of the failure. Yeah, it's a perfect analogy.
Because the compute is there.
The compute capacity, the physical shelf space to do the math, is technically there on the chips we are deploying today.
Right.
But the moment you start utilizing that capacity for heavy, continuous AI inference, the heat generated by moving the data through the silicon exceeds the cooling capacity of the store.
The refrigerators blow out.
Right. The system thermal spike, the hardware aggressively throttles its own clock speed just to prevent itself from melting, the AI slows to a total crawl, and eventually the entire system fails.
Which means if we can't just shove a massive power-hungry air-conditioned server rack into a radio tower due to these thermal limits, we have to fundamentally rethink the silicon running inside the edge devices themselves.
We have to.
Because we can't change the ambient temperature of the sun in Nagpur.
No, we definitely can't do that.
So we have to completely redesign the chips.
And that brings us to the actual engineering reality of the hardware.
Let's get into the hardware.
So, to understand how we actually fix this thermal issue, we have to look at the findings from Google's 2021 Edge TPU characterization study.
This was a massive study.
Huge.
Oh.
Google ran an exhaustive study across 24 different neural network models, everything from basic object detection to complex natural language processing.
And what were they trying to find?
They wanted to figure out exactly where the bottleneck was occurring on edge hardware. Why was it slowing down? Why was it overheating?
And what they found completely upends how most people think about processor speeds.
Oh, totally.
Because the dominant engineering bottleneck in edge AI is not raw compute throughput.
It's not the processor at all.
Right. It's not about how many floating point operations per second or FLOPS the chip can theoretically execute. The bottleneck is memory bandwidth.
Yep.
It is the sheer energy cost of physically moving data from one part of the chip to another.
The Google study revealed that edge devices are operating significantly below their peak computational throughput in the field.
So they aren't even maxing out their math capabilities.
Not even close. The processors are essentially starving. They just sit idle for millions of clock cycles, fully capable of doing the complex math, but they are literally just waiting for the data to arrive from the memory banks.
Okay, let's get into the physics of this for a second. Why is moving the data generating so much heat? This comes back to the von Neumann architecture, right?
Exactly. The von Neumann architecture is the foundational blueprint for almost all modern computing.
We've been using it for decades.
Right. And in this system, the processor, the part doing the actual calculations, and the memory, the part storing the data, are physically separated.
They are on different parts of the board.
Yeah. So to execute a calculation, specifically a multiply accumulate operation or an AFC operation.
Which is the core math of a neural network.
Right, the core building block. So to do that one operation, the processor has to send a signal across a physical wire, a bus, to the memory. It fetches the weight, pulls it all the way across the bus, does the math, and then pushes the result back across that exact same bus.
And driving an electrical current across that physical wire billions of times per second creates friction.
Lots of friction.
Which creates heat.
It creates immense heat. Shuttling that data back and forth actually costs vastly more energy and takes significantly more time than the actual mathematical calculation itself.
Wait, really? Moving it costs more than the math?
Oh, by a wide margin.
Yeah.
In modern edge chips, accessing off-chip DRAM can consume up to 200 times more energy than performing a single floating point operation.
200 times?
Yeah. Moving the data is what is melting the system, not the math. This is known in the industry as the memory wall.
The memory wall. So if you are an operator deploying hardware, this completely changes your purchasing and testing decisions.
It has to.
The sources reference the Rochester Institute of Technology's Energy Accuracy Trade-off Framework.
Right? A very important framework.
Because if you are dealing with battery-constrained IoT devices or these highly thermally constrained 5G base stations we've been talking about, adding a faster processor without fixing the memory architecture actually makes your deployment significantly less reliable.
Because if the processor is faster, it demands data faster.
Oh, I see.
Yeah, which means you are trying to push even more data across that narrow memory bus in a shorter amount of time, which spikes the energy consumption exponentially and accelerates the thermal throttling.
You are essentially generating more heat without getting any more actual AI inference done.
Exactly. You're just backing up traffic faster.
That's incredible. And the sources mention that researchers at the University of Padova have developed empirical models specifically for NVIDIA edge boards that allow operators to accurately estimate these exact energy deployment costs.
Yeah, the Padova research is super practical.
They are mapping out the exact energy cost of a specific neural network layer before the hardware ever leaves the lab.
Which leads to a core actionable protocol for operators.
Okay, what's the protocol?
When you are validating edge hardware, you must aggressively profile the memory system's energy usage, not just the raw inference speed that the vendor advertises on the spec sheet.
Right, ignore the FLOPS on the marketing brochure.
Exactly. If your memory bus is saturated during a continuous video processing loop, the system is going to overheat and fail. It absolutely does not matter if the CPU is theoretically capable of 100 teraflops if the memory bus can only feed it enough data to process 10 teraflops.
So this is like having a massive 500 horsepower engine in a race car, but the fuel line feeding that engine is the size of a tiny plastic coffee straw.
Another great analogy, yes.
It doesn't matter how fast the engine could theoretically run or how much fuel is in the tank. The engine is starving because the delivery mechanism is choked. So how do we widen the straw?
Well, here's the thing. You don't.
You don't.
Widening the straw still requires pushing fluid through a pipe, which still takes energy and generates heat. The cutting-edge solution the industry is pivoting toward isn't widening the straw. The solution is to move the engine directly inside the gas tank.
Okay, moving the engine into the gas tank. That brings us to processing in memory, or PIM architectures.
Yes, PIM.
How does this physically alter the chip design?
Processing in memory directly attacks that von Neumann memory wall by fundamentally changing the geography of the silicon itself.
So it's a structural change.
Exactly. Instead of having a separate processing chip and a separate memory chip, PIM embeds the compute units, the actual logic gates, doing the math directly inside or immediately adjacent to the DRAM arrays.
Oh, wow.
Yeah, you are collapsing the physical distance the data has to travel down to the microscopic level. You eliminate the long physical bus entirely.
The PatSnap Technology Landscape Report highlights an ETH-Zurich analysis from 2022 that compares 3 specific PIM variants, and this is where the physical engineering gets incredibly granular.
So they really dug into it.
They analyzed UPM, which uses 2D chip integration. They looked at Mensa, which utilizes 3D stacking specifically optimized for the edge. And they looked at SIMDRAM, which approaches the problem using analog bit serial computing.
And the reason this matters deeply to an operator is that PIM is exceptionally effective for memory-bound inference workloads.
Which is most of what we do at the edge.
Right. If you look at the vast majority of AI tasks happening at the edge today, transformer models parsing text, or convolutional neural networks doing computer vision, object detection, voice recognition, they're almost entirely memory-bound.
They require pulling massive amounts of weights from memory for every single frame of video.
Exactly.
Let's break down that Mensa variant, the 3D stacking approach. How exactly does 3D stacking fundamentally change the thermal output of the chip?
Well, think about traditional 2D chip integration like a sprawling suburban city.
Okay.
The memory arrays, the logic cores, the cache, they all sit side by side on the flat silicon wafer.
Spread out.
Right. And because they are spread out horizontally, the physical wires connecting them have to be longer. Longer wires mean more resistance, which means higher voltage is required to push the signal, which results in more heat.
And Mensa changes that geography.
Mensa uses 3D stacking, which is like building a skyscraper instead of a suburb.
Oh, I see.
The manufacturer physically stacks the memory dies vertically directly on top of the logic die.
So the memory is quite literally sitting on top of the processor.
Yes. And to connect them, they use something called through-silicon vias, or TSVs.
TSVs.
These are microscopic, vertical copper pillars punched straight down through the silicon layers. So instead of a piece of data traveling millimeters across a horizontal bus, it travels micrometers straight down a vertical TSV directly into the logic core.
The physical distance collapses.
Completely.
And the resistance plummets. And the energy required to move the data practically disappears. The data just drops through the ceiling, so to speak.
Exactly. It just drops right in. And because the energy required to move the data drops so dramatically, the overall thermal footprint of the chip drastically shrinks.
It generates a fraction of the heat while doing the exact same amount of work.
Which is massive for the edge. Suddenly, you have a physical hardware solution to that base station cooling issue we discussed regarding the Nectar's summer heat.
Right.
You don't need a massive industrial air conditioner for the enclosure if the chip itself isn't generating the heat in the first place.
That is incredibly elegant. The sources also highlight something radically different coming out of the University of Kentucky called the ATRA system.
Oh, ATRA is fascinating.
It uses something called stochastic arithmetic to execute 16 MSE operations per 5 memory cycles.
Yeah.
What exactly is stochastic arithmetic, and how does it save memory cycles?
This is a brilliant departure from traditional computing. Normally, chips use deterministic binary arithmetic, right?
Right, ones and zeros.
A specific string of bits represents a specific number, like a 32-bit floating point value. But doing complex multiplication with 32-bit numbers requires thousands of logic gates.
Okay.
Stochastic computing represents numbers not as exact bit strings, but as probabilities in a stream of random bits.
Wait, probability. So instead of a rigid number, it's measuring the frequency of ones and zeros in a stream.
Precisely. If a stream has 70% ones and 30% zeros, it represents the value 0.7.
Oh, that's clever.
It is. And the massive advantage here is that you can multiply 2 stochastic bit streams using a single microscopic logic gate, an AND gate.
Just one gate.
Just one. You replace thousands of power-hungry logic gates with one single gate.
Wow.
The ATRIA system leverages this to process massive amounts of mathematical operations directly near the memory banks while taking up an incredibly small amount of physical silicon space and generating almost zero heat. The efficiency advantages for edge AI are astronomical.
So the actionable takeaway for operators looking to future-proof their edge testing environments is extremely clear here. You must begin benchmarking your specific workloads against PM simulators today.
Today, do not wait.
You cannot rely on traditional von Neumann benchmarking metrics if your future hardware is going to be structurally and geographically different. You need to prioritize evaluating architectures like Mensa and ATRA, particularly if your deployments rely heavily on continuous computer vision applications.
Yeah, because if you wait for the physical PM chips to become fully commoditized before you start testing your software against their architecture, you will be years behind the deployment curve.
But as an operator, my operational alarm bells are kind of ringing right now.
Oh, why is that?
Well, we are talking about hardware getting wildly efficient by physically blending the memory and the compute together into these incredibly dense, specialized, vertically stacked 3D chips.
Right.
But if the hardware is that rigidly specialized, doesn't that make updating the software an absolute nightmare?
No.
I mean, historically, you train a massive neural network in a giant cloud data center, freeze it, and push that static finished version down to the edge device just to run the inference.
The traditional way.
Right. But if we need these edge devices to adapt to their environments, how do you dynamically update or train a neural network on a chip where the memory and the processor are practically baked together in a physical skyscraper format?
That is the exact friction point the entire industry is pivoting to solve right now.
It seems like a massive hurdle.
It is. The challenge is no longer just running inference at the edge. It is creating methods to dynamically adapt and even continuously train AI models directly on these highly constrained, specialized edge devices.
Without breaking them.
Right, without breaking the system, causing a thermal overload, or exposing the network to severe security threats.
So we are talking about the transition from static edge inference to active, continuous on-device training.
Yes.
And the sources point to some fascinating breakthroughs here, specifically a 2024 paper from A-Star Singapore focusing on RCT, or resource-constrained training.
Yeah, the A-Star paper is a major breakthrough.
They developed a method utilizing quantized model-only training that allows the training process to fit entirely within the on-chip memory. Why is fitting the training process entirely on-chip the holy grail here?
To understand why this is a breakthrough, you have to understand why training an AI model is vastly more expensive than just running it.
Okay, break that down for us.
When running a model, just doing inference data just moves forward through the network. It's a one-way street.
Simple.
But when training a model, the system has to perform a backward pass to update the weights based on its errors. This backpropagation requires storing massive amounts of intermediate data, called activations, for every single layer of the network.
And in a normal setup, those activations are far too large to fit in the small, fast memory next to the processor, right?
Exactly. So they get pushed out to the off-chip DRAM.
And as we established, moving massive amounts of data off-chip and back on-chip creates immense heat and drains the battery instantly.
It hits the memory wall. But the A-Star team solved this using quantization. Instead of storing these activations as massive, precise 32-bit floating point numbers, they compress them down to 8-bit or even 4-bit integers.
So they intentionally lower the mathematical precision of the data.
Yes. And by doing that, they compress the size of the training data so drastically that it can sit entirely inside the on-chip SRAM, the super-fast memory sitting right next to the logic cores.
Oh. They eliminate off-chip data movement entirely.
Entirely.
Which obviously solves the thermal and energy issues we discussed. But the sources also indicate this has a massive impact on physical security.
It absolutely does. This is a huge point for operators.
Why does it help security?
Well, every time data leaves the internal chip architecture and crosses a physical motherboard bus to reach an external memory module, it can be physically intercepted or sniffed by an attacker with hardware access.
Oh, because the data is literally traveling across a wire on the board?
Exactly. If I have physical access to the street lamp, I can tap that bus. But by keeping the continuous training loop and all the sensitive local data it is learning from entirely on chip, you drastically reduce the surface area for cyber attacks.
Because it never leaves the internal logic.
Right. You are effectively training a bespoke AI model inside a sealed microscopic silicon vault.
That is incredible.
Hmm.
But mapping these complex, quantized training algorithms onto these specialized new chip architectures isn't something a human engineer can just sit down and write in an afternoon, is it?
Oh, definitely not. It's practically impossible for a human.
Which ties directly into what the Shanghai Jiao Tong University researchers are doing with hardware-software code design via NAS, or Neural Architecture Search.
Oh,
Specifically, their NAS framework.
yeah, NAS. This is where we hand the engineering over to the AI itself.
AI building AI.
Exactly. NAS stands for Neural Architecture and Accelerator Search. In the past, hardware engineers would design an edge chip, and then software engineers would try to manually tune a neural network to run efficiently on it.
And it was just trial and error.
It was a massive, incredibly complex game of trial and error that took months.
But NAS automates the entire stack.
It does. It uses an AI algorithm to jointly search the neural network architecture, the physical accelerator architecture, and the compiler mapping all simultaneously.
So it's juggling all three variables at once.
Right. The AI evaluates millions of different configurations, like should we use a deeper network with fewer channels? Should we allocate more silicon area to the memory buffer or the compute array? How should the compiler tile the data into the chip?
And the results from the study are a wake-up call for the industry, because the NAS framework achieved a 4.4x energy delay product reduction compared to the Iris.
Yes, and Iris was a state-of-the-art accelerator designed manually by some of the best human engineers in the world at MIT.
And the AI beat it by 4.4 times.
It wasn't even close. It proves unequivocally that manual hardware-software tuning is officially obsolete. Human engineers simply cannot hold the multidimensional complexities of these specialized edge chips and neural networks in their heads simultaneously.
You must use AI to map the AI onto the silicon.
It's the only way forward.
But this introduces an operational nightmare for the person actually tasked with testing this infrastructure.
Oh yeah, testing it is a whole different beast.
Right, because if an AI is constantly tweaking the neural network architecture, how does an operator validate the system latency? Profiling Ed's hardware exhaustively in a lab for every single micro tweak a neural architecture search generates is impossibly expensive and slow.
Which is exactly why the industry is building virtualized cost modeling.
Like Maple Edge.
Exactly. The sources highlight solutions like Maple Edge from Darwin AI.
Yeah.
Instead of physically running millions of different model architectures on a piece of hardware, like an NVIDIA Jetson board, to see how long they actually take.
Because that would take years.
Right. Maple Edge uses specialized regression networks to accurately predict the latency.
So they train an AI to predict how another AI will perform on a specific piece of hardware.
Exactly. It completely removes the need for exhaustive, expensive physical hardware profiling. An operator can model the latency virtually, instantly, and with extreme accuracy.
Which allows the neural architecture search to find the optimal design without ever leaving the simulation environment.
Boom. Exactly.
But we have to address the reality of managing this at scale, because the Technalia 2023 security framework explicitly states that security must be a first-class design constraint, not an afterthought bolted on at the end.
Right, especially when we were talking about pushing dynamic learning AI models to highly distributed, often physically exposed locations.
Like street corners and oil rigs.
Exactly. And this is where the edge management platforms, the EMPs highlighted in the Technology Radius report, become mission-critical infrastructure.
How so?
Well, managing a single static AI model on a camera in a lab is easy.
Yeah.
But managing 500 different models, all continuously learning, dynamically adapting their own architectures, and updating their weights across 2,000 secure, physically air-gapped industrial sites.
Yeah, you cannot do that manually.
No. The report specifically highlights AWS IoT Greengrass for making cloud services behave consistently down at the edge level. But more crucially for security, it highlights ZIA for Zero Trust Remote Management, particularly in heterogeneous, chaotic industrial environments.
Okay, zero trust. But zero trust at the physical edge is fundamentally different than zero trust in the cloud, isn't it?
Oh, completely different. In the cloud, the physical servers are secured by armed guards and biometric locks in a bunker somewhere.
Right.
At the edge, a bad actor can literally walk up to a smart traffic light, physically break open the box with a crowbar, and plug a USB drive directly into the hardware.
That is terrifying.
It happens. So ZDITA provides a distributed orchestration plane that assumes the hardware itself operates in a hostile physical environment. It ensures that even if a continuously learning AI model is completely severed from the cloud, it can securely update, train, and execute locally without trusting any external inputs it hasn't cryptographically verified.
And the management platforms also have to handle dynamic resource allocation, right? The sources outline the concept of InstantNet, which generates variable bit-width neural networks. What does that look like operationally?
It means the AI model is actually capable of adapting its own mathematical precision in real time to match the fluctuating physical resources of the IoT device it lives on.
Give me an example.
Okay, so say the battery voltage of a remote sensor drops drastically, or the ambient temperature spikes, like our NAG core example, and the chip needs to cool down instantly to survive.
What happens?
InstantNet dynamically shifts the neural network from 8-bit precision down to 4-bit precision on the fly.
It just dumbs itself down a little bit.
Exactly.
Yeah.
The model becomes slightly less accurate, but it consumes dramatically less power and generates less heat, allowing the device to survive the environmental stress event without completely shutting down or melting.
That is incredibly resilient. So the concrete takeaway for the operator is this. To validate on-device training reliability securely, you cannot rely on physical lab testing alone. You must utilize NAS cost modeling, like Maple Edge, to test your latency virtualizations.
Right.
And you absolutely must implement platforms like ZData to ensure zero-trust offline operations when you are deploying these continual learning models into the physical world. The management plane and the virtualized testing are just as vital as the silicon itself.
Because you are no longer just deploying software, you are building a localized, self-contained, adaptive ecosystem.
But let me pause and channel the skepticism of a seasoned operator right now,
Go for it.
because this entire architecture sounds incredibly fragile.
I know it does.
I mean, we are talking about AI models rewriting themselves, compressing their own activations, continuously training on tiny vertically stacked 3D chips, dynamically altering their own bit-width precision based on fluctuating local temperatures, and doing all of this completely isolated from the centralized cloud.
It's a lot of moving parts.
In a sterile, controlled laboratory environment, that sounds like brilliant computer science. But out in the real world, where you are dealing with torrential rain, physical damage, erratic power grids, and unpredictable physical chaos, how is an architecture this complex actually surviving contact with reality?
It is a profoundly valid concern. It sounds like science fiction that would break the moment it gets rained on.
Exactly.
But the answer isn't theoretical. The reality is that this highly decentralized adaptive architecture is not only surviving contact with reality, it is already being deployed as the foundational infrastructure in the most high-stakes life-or-death environments on the planet.
Which brings us to our final operational reality for this deep dive. Mission-critical production, where edge inference restores physical reality.
Yeah.
The sources highlight specific, critical sectors that have already abandoned centralized cloud reliance for these exact edge architectures. In the automotive sector, we see ZF Friedrichshaffen's Pro AI platform specifically targeting ASIL certification.
Now, ASIL stands for Automotive Safety Integrity Level.
Right.
It is one of the most rigidly unforgiving risk classification schemes in the world. You do not get ASIL certification by relying on a cloud server in a different state to tell your autonomous vehicle's brakes to engage.
Because if the cell tower drops.
Exactly. The latency and the risk of network failure are entirely unacceptable when human lives are at stake. The intelligence must reside natively on the vehicle's own silicon, processing LiDAR and camera feeds in milliseconds locally.
And the aerospace sector is dealing with even more extreme constraints. The European Space Agency's FISAT-1 is using edge inference to physically filter out useless cloud-covered imagery directly on board a satellite in low Earth orbit.
Think about the physics there. The bandwidth required to downlink high-resolution hyperspectral imagery from orbit to a ground station is incredibly expensive and extremely slow.
Right.
So if 70% of the images a satellite takes are just pictures of opaque weather clouds,
Sending those images back to Earth is a massive waste of resources.
a total waste. FISAT-1 uses a highly constrained, thermally hardened edge AI chip to process the imagery in real time, discarding the useless photos in space and only utilizing the precious downlink bandwidth for clear, actionable data. It is the ultimate expression of moving compute to the data.
Literally moving compute to space. We also see this in scientific infrastructure, like the Fermilab particle accelerator, where the data generation rate is so astronomically high that it is physically impossible to move the raw data to a standard server for processing.
Right? They have to process it locally because the volume is too massive.
But to truly understand how an operator architects a system like this for the real world, we need to break down the telco-powered SmartX intersection safety architecture detailed in the AWS documentation.
Oh, this is my favorite example.
Because this isn't a single device, it is an entire ecosystem operating in real time. Let's walk through this millisecond by millisecond, because this illustrates exactly how the multi-tiered distributed architecture proves its worth.
Walk us through it.
Okay, imagine a busy, chaotic urban intersection. The city has instrumented this intersection with high-definition cameras and roadside units, or RSUs.
So at what we call the far edge, the physical camera enclosure and the RSU bolted to the traffic pole, you have highly efficient local inference running on embedded CPU and GPU hardware.
Right.
These far edge devices are running specialized vision language models, or VLMs, actively interpreting the live video feed locally.
Now, a vehicle runs a red light and is on a direct collision course with a pedestrian stepping into the crosswalk.
A critical event.
If this architecture relied on the cloud, the camera would encode that video, push it across the 5G network, route it through several internet exchanges, process it in an AWS server hundreds of miles away to ask, is this a crash? And then send a command back to the intersection to trigger an alarm.
And that cloud round trip, even on a perfectly optimized day, takes tens or hundreds of milliseconds.
Which doesn't sound like much.
But when a vehicle is moving at 45 miles per hour, hundreds of milliseconds equal dozens of feet. The latency tax of the centralized cloud is the literal difference between the car stopping in time and a fatal impact.
So how does the edge architecture handle it?
The far edge device utilizes what the AWS memo calls a simple reflex agent.
A reflex agent.
Yes. It isn't trying to understand the complex behavioral patterns of city traffic. It is simply looking for an immediate physical anomaly, two trajectories intersecting.
Keep it simple, keep it fast.
Exactly. The moment it detects the anomaly, the reflect agent triggers an instantaneous response entirely locally, usually in under 10 milliseconds.
10 milliseconds.
Yeah. It bypasses the wider network entirely, immediately turning all intersection lights red and broadcasting a low-latency V2X vehicle to everything warning directly to the braking systems of surrounding cars.
But the processing doesn't stop there, because the reflex agent kept the human alive, but the system still needs to understand what happened.
Right.
This is where the multi-agent collaboration workflow kicks in. That reflex agent at the far edge instantly alerts a semi-autonomous agent sitting at the near edge.
And the near edge, in this specific architecture, is the 5G MEC base station sitting a few blocks away.
The one we talked about earlier.
Right. The base station has significantly more compute power and thermal headroom than the camera on the pole. So it receives the alert and immediately aggregates the video feeds from all the other cameras at that intersection to validate the collision trajectory.
It provides the necessary situational context.
Exactly. Did a car actually run the light, or did a plastic bag blow in front of the camera lens, triggering a false positive?
So the near edge validates the reality of the event, and only then, after the immediate danger has been mitigated and the event has been contextualized, is the data forwarded to the cloud. But it isn't sending the raw, heavy video files.
No, never. It only forwards enriched, highly compressed, vital metadata up to the autonomous agent running in the centralized AWS region cloud.
What does the cloud do with it?
The cloud is strictly reserved for post-perception analytics and long-term orchestration. The autonomous agent in the cloud receives the metadata from this intersection, cross-references it with data from hundreds of other intersections, and uses that massive compute power to adjust long-term, city-wide traffic light timing policies.
So it coordinates regional emergency dispatch systems and continuously fine-tunes the master AI models that will eventually be pushed back down to the edge hardware.
Exactly. It's an ecosystem.
This tiered architecture connects deeply to the core philosophy outlined in the founder strategy memos, restorative engineering.
Yes, restorative engineering.
The concept that technology shouldn't just process data for the sake of processing data, or simply to build a massive dashboard in a cloud operations center. True restorative engineering dictates that you must keep the intelligence as physically close to the consequence as possible.
There is a profound story in the memos illustrating this perfectly.
The cobot story.
Yes, an integration team was deploying a TechMan cobot, a collaborative robotic arm equipped with sophisticated built-in vision systems into a highly dangerous manufacturing facility.
And the danger wasn't just heavy machinery.
No, the factory workers were literally handling and assembling live ordnance, live grenades.
Oh, wow.
And the crucial point the founder makes is that this multi-million-dollar robotics system wasn't deployed to disrupt the assembly line. It wasn't deployed to gather massive granular data sets on worker efficiency to send back to a centralized AWS dashboard so executives could optimize the supply chain.
No.
The intelligence was deployed specifically to process the physical risk, right there in the room. The vision system ran entirely locally on the robot, constantly analyzing the state of the live ordnance and the position of the human worker.
The intelligence was kept intimately close to the consequence.
Exactly. It allowed the human worker to walk out of that facility at the end of their shift
Okay.
and say, I am safe tonight. That is the ultimate uncompromising metric of restorative engineering. It is technology actively restoring order and physical safety to the chaotic physical world.
So if you are the operator tasked with testing and validating reliability for mission-critical edge deployments, your fundamental takeaway is structural.
It has to be.
You must architect multi-tiered fail-safes. You must have a rigid reflex agent engineered at the specific device level, the far edge guaranteeing that sub-10 millisecond response for immediate safety.
Yep.
You must provision a secondary semi-autonomous agent at the local base station, the near edge, to provide the contextual processing. And you must strictly limit the centralized cloud to post-perception analytics and long-term orchestration.
If your system requires an active connection to the cloud to make a split-second, life-or-death physical safety decision, your architecture is fundamentally flawed.
Period.
Period. And your testing framework should reflect that as a critical failure.
Yeah. Wait, so true reliability isn't about making a single device invincible or guaranteeing 100% uptime on a cloud connection. It is about designing an ecosystem where the most critical, consequential decisions are naturally processed closest to the danger.
Absolutely.
It's exactly like human reflexes. If you accidentally put your hand on a burning hot stove, you don't actively consciously think about pulling it away.
Right, you don't ponder it.
The pain signal doesn't travel all the way up to the cognitive processing centers of your brain so you can evaluate the temperature and decide on an action. Your spinal cord receives the signal and instantly triggers a reflex action to pull your hand away, completely bypassing the brain. The brain only gets the metadata later to say, ouch, don't do that again.
That is exactly it. We are essentially building a decentralized nervous system for the physical world.
A nervous system.
Yeah. The far edge, the camera, or the sensor, is the nerve ending detecting the immediate threat. The 5G MEC base station is the spinal cord executing the rapid contextual reflex. And the centralized cloud is the brain, receiving the post-event metadata to learn from the experience and adapt long-term behavior.
All right, let's step back and look at the massive expanse we have covered today.
We really went everywhere.
We did. We started by looking at the strategic boardrooms, decoding the hidden war between the telecommunication operators and the hyperscalers. We examined the dumb pipe dilemma and established how the unyielding thermal realities of 5G infrastructure, the physical impossibility of cooling a massive server rack in the sweltering Nagpur heat, is forcing a total architectural shift.
Right.
We drilled all the way down to the microscopic level of the silicon itself, detailing how the von Neumann memory wall is physically starving processors, and how processing and memory architectures like Mensa and ATRA are physically embedding the compute engine directly inside the memory array to eliminate the friction of data movement.
We also explore the complex software realities required to manage this new hardware. We looked at how A-Star's quantized model-only training fits complex learning entirely within on-chip's RAM, right?
Right.
And how neural architecture search algorithms are definitively rendering manual human hardware tuning obsolete. And, of course, why edge management platforms like ZData are non-negotiable infrastructure for maintaining zero-trust security when deploying continuously learning adaptive AI into hostile physical environments.
And finally, we zoomed all the way back out to the real-world, life-saving consequences of mission-critical production, from satellites filtering hyperspectral imagery in low Earth orbit, to the restorative engineering philosophy keeping a factory worker safe while assembling live ordnance, to the millisecond by millisecond multi-agent orchestration preventing a fatal collision at a smart intersection.
The inescapable truth connecting all these sources is this. Real technology doesn't just overlay a digital simulation onto the physical world. It actively restores functional order to it.
It has to function in the real world.
If you are an operator or an engineer tasked with building for the edge, you must build for the unrelenting physics of the edge. You must rigorously respect the thermal limits of the enclosure, you must architect around the energy costs of the memory wall, and you must adhere to the absolute necessity of keeping the intelligence as physically close to the consequence as possible.
Which brings us back to the premise that sparked this entire deep dive. We have built the largest distributed physical network in history, and for a very long time, we allowed it to remain functionally brain dead, acting as nothing more than a dumb delivery mechanism for the cloud.
But that era is ending rapidly.
The intelligence is actively migrating outwards. It is moving into the 5G towers, it is embedding itself into the street cameras, and it is actively controlling the robotic joints on the factory floor.
It's all moving to the edge.
And I want to leave you with a final, highly provocative thought to consider as you go back to your labs, your deployment maps, and your testing frameworks.
Give to us.
If the future of artificial intelligence is inherently and necessarily highly localized, if it is structurally thermally constrained, and if it is specifically designed to operate autonomously on decentralized physical networks without relying on an internet backbone, what happens to the massive centralized multi-gigawatt cloud data centers we are pouring hundreds of billions of dollars into building right now?
Yeah.
Are we currently investing trillions of dollars into the artificial intelligence equivalent of massive room-sized mainframe computers right on the very eve of the personal computing revolution?
That is the multi-trillion-dollar question that will define the next decade of infrastructure.
Thank you for joining us on this deep dive. Stay curious, always build for the physics of the real world, and we will see you next time.